Blockchain is the hottest market around. The quickest way to succeed is with an application that delivers information that lets your users act a step ahead of everyone else. However, finding and sending that information can be tricky and costly. The right data solution grabs current and historical price and volume data from relevant market services. It crunches that data straight from the blockchain to produce on-the-spot buy and sell indicators, generating averages and algorithms for immediate market opportunities. At predetermined time intervals, it sends that data to analytical business intelligence solutions like Grafana, filling up data lakes to produce deeper market insights. A native MapReduce creates rolling aggregates to update probability matrices in real time. Automatic indexes get your info faster than anyone else with data that is completely accurate, delivering all fully transactional asset integrity promises. Lightning fast performance for data subscription comes in handy when that big buy signal comes, so your application can make the trade before the market corrects it away. After all, we're dealing with your users' money. Today, Federico Lois, a veteran of blockchain applications, will show you how to use RavenDB's basic database features to convert raw blockchain data into your next cooked steak. Feel free to ask questions by clicking the Q&A button at the bottom of your screen, and Federico will be happy to answer them throughout the session. Enjoy your presentation, and here's Federico.
Hello, everybody. How you doing? Let me first share my screen so we are actually able to talk about specifics. So I presume you're already watching the presentation. So the idea of this talk is to talk about specifically how to build competitive blockchain applications, because let's face it, we're going to be talking about blockchains specifically, but the most important part of it is to understand that databases that are designed to become blockchain solutions are actually not that good to do everything that has to be done around them, which is the analyzing part of it. So let's start with the basics, and then we will move straight into actually a demo of how that kind of applications could be done. So for the basic, for everybody that is around, it is very, very important to understand what is the blockchain, okay? Because there's the blockchain this, the blockchain that, and in the end, we need to understand essentially what that means. What are the key components that make a network of distributed computers able to create a blockchain? So the blockchain, to think it in a way, it's essentially fusing three important concepts. One concept is cryptography. Blockchain solutions would not be able to exist without cryptography, without the capability for someone to say, I did this, and on the other side, everyone else said, yes, he is the one that says that did this, and he also did that. And essentially, that's been done through originally in the Bitcoin network through a proof of work, which essentially means I am solving a problem which is asymmetric. With asymmetric, it means that to solve the problem, it actually costs much more energy than for someone else to actually verify that I solved the problem. For that, and that's essentially the reason why there has been a very, very strong movement now to move into a different kind of technology, which is proof of stake. And the reason is essentially the amount, as the price of the underlying assets go up, more people wants to get in. And the actual cost that the proof of work generates, and the actual cost in energy that it translates directly into consumption of energy and resources. So it doesn't make a lot of sense just to run the entire electricity output of California to sustain a blockchain. So proof of stake is essentially the same idea, but with a different mechanism in which you essentially say, okay, I have these assets, then I'm going to put those assets in there. Like I'm saying, I want to be part of this network, so I'm willing to put some collateral in the financial sense to say that I'm be willing to abide by the rules, which means that if I break the rules, I can actually lose the collateral in the process. So it's pretty interesting how the mechanic of if I do something that is bad for the network, I'm actually can get punished from it, which is a mechanic that really doesn't exist on the proof of work. And the reason why certain things like, for instance, mining pools, which are lots of people that join their resources to actually solve these distributed problems. If they get, for instance, in the Bitcoin protocol, if some pool gets 51% of the entire computing power, then we are in trouble. And it actually happens a few times. On the other side, the other important concept, which is I hinted here, talking about the proof of work and proof of stake, is actually the decentralized network. If the power is centralized on a single user or in a single group, then there's really no reason, there's no difference between thinking, for instance, that this Bitcoin as a central bank, in a sense, because it's about money. So if that single entity can have all the resources, they can essentially decide what to do with it. There's no consensus possible because there's a single entity that can actually monopolize that consensus. But the reason why all these three concepts are important is because they allow to build a distributed database driven by consensus. So with a distributed database, and you know, we are here with hibernating rhinos, which builds a database. Well, this is a different type of database. This is a database built on top of these concepts to actually support highly distributed consensus. Okay. So the idea of this is there's not a single database. And this is important because when you talk about Bitcoin, Bitcoin is just one single blockchain. And actually, if you think about it, Bitcoin, which is like the primordial, is the first that it existed there, is actually not Turing complete, which means that it was designed as a way to decentralize money. So every concept that exists in that network, in that database, exists around money. So you can send and receive money, create accounts, create wallets. They're called in the crypto environment. But the thing is that everything is about money. Now, there are other types of blockchains. Probably the most known and most used around is the Ethereum blockchain, which is actually Turing complete. What it means is that essentially you can build any potential program that you want to be running this distributed network and be stored physically in this network forever. So whenever you create a Ethereum, a program that runs on this big machine, because essentially Ethereum is a machine, it's a big distributed machine that can run programs and store its state in the blockchain. So for doing this, you use, for instance, the Solidity language, and because of this ability to essentially design everything, to be able to execute anything that you can think of, it's actually perfect for smart contracts. And the reason I use smart with the quotes here is that essentially smart, they are not really that smart. They're essentially programs. And you know what happens with programs. Programs will execute exactly what you say that they need to be executed. And conditions are not necessarily complete. So what happens there? You essentially create loopholes. for everyone that has been following the history of the Ethereum network, some may remember that there was a hard fork along the way where Ethereum Classic, which is the original, in a sense, the original Ethereum, gets forked because essentially some of the developers didn't work to fix a mistake in a program. Some of the developers decided that, hey, because this program that it's being used, a loophole in this program is being used to actually extract the money from a DAO, from a contract in a way that it was not designed to happen. This group of developers says, no, we cannot allow this because this is essentially stolen money. So what they do is essentially fork the network, and some people say, no, we don't want this situation. We don't want to have everybody deciding that some transactions need to be reverted. So essentially that fork can create two different blockchains. One where this original sense of if it's written in the blockchain is done, which is Ethereum Classic, and this new, where there's actually some kind of consensus regulation in place, which is the actual Ethereum blockchain. So the idea of the blockchain and why we call it blockchain is because of its structure. Blocks are the primary structure of the blockchain, and essentially what they do is like a sequence of blocks that are going to tell you at this point in time what is essentially the truth for a particular object in the network. So those objects, so those states move discretely, and those blocks are actually linked together using cryptographic signatures in such a way that when this is written into the network, essentially what you will get is a actual this is the state that everybody, this is the consensus that everybody have about the state of the world at this point. So if someone tries to change anything, everyone will notice that, because the signatures of the cryptographic signatures will not match. So this is how when you do something, when you execute something, you are able to be detected if you want to tamper with the data. The blocks also contains batches of transactions, and really the transactions is where the action really happens. Transactions are essentially the bread and butter of what is happening, because those are the state changes in the world. So as you can see here, you have the world state as it was 10 minutes ago. Then a miner will solve this distributed problem using this group of transactions and be rewarded for that. And then after this happened and consensus is we arrive to consensus, then we know that the new world state is going to be this +1, and this is the absolute truth now. So while this may seem like abstract, it actually exists as is. We are going to be going to one very useful application, which is called Etherscan.io, which allows you essentially to look into that particular thing. So as you can see here, these are the latest blocks. This block was generated 32 seconds ago, and this one 35 seconds ago. If we go and look at it, what we essentially are able to look is into the actual representation of this block, which tells you essentially which position, which time t. This is the block number, is the actual time t of this block. So when did this when it was created and how many transactions there are. Actually, this is a very uninteresting blocks with 0 transactions, 0 contracts. Anyway, so let's look for a different one. Okay, so this one is more interesting because it has more transactions in it. Let me show it. So we actually have 114 transactions with 24 contract internal transactions in the entire block, which was mined by this address, which was rewarded with this particular amount of ether. In the Ethereum computer, people actually get rewarded with ether. Ether is the currency in which this the transacting currency for this particular computer. And how this ether is composed? It's essentially composed of, okay, you have two ether for the reward, but you also have collected 0.46 ether from the actual transaction execution. So because you executed those transactions in these computer, essentially you are rewarded with those transaction fees. There's also, this is also pretty new, which is how you deal with inflation in this type of systems, which is actually what is called the VARN transaction. So every transaction since I think August last year, remember, actually burns some of those fees, and they are never ever going to be able to be accessible again. This is because if you're constantly rewarding 2 per block, essentially what would happen is that the actual amount of ether would grow linearly. But the usage of the computer itself may not go linearly like that. So essentially, this works as a financial way to get rid of that excess from the expected usage that you should have for that amount of for the amount of circulating currency. This big number is actually the difficulty to solve this particular thing, and it's interesting because this also is the problem with proof of work. When this difficulty goes up, it actually means that the work that is required to actually being able to find these to solve this problem is essentially a problem in itself. Just to illustrate, this is me running a mining algorithm on a different blockchain with a different algorithm, but essentially what you will see here is that I'm running and I'm solving problems with different levels of difficulty. For some reason, I found this one, which is pretty good. If you look at the one that I shared here, has like 2 zeros less. So in this one, to solve this one, I was actually very lucky. So the idea of here is that you are using your particular hardware to solve this problem instead of staking your assets to do so. So, as I mentioned, this is a machine, and because it is a machine, essentially what you would do, what you have is actually you have your quota. Okay, every machine, every block has a quota of the share of the machine that it can be used, and this is essentially the gas. Every block has a gas limit of 30 million. Now, it's interesting to note that these 114 transactions with 24 internal contracts actually use 7 million of that gas instead of the entire 30K. The idea is to avoid this situation in where someone with a high too much computing power can actually goes over the gas limits and monopolize. Okay, so if you're able to compute so fast that you can achieve that, you can pack more transactions. If you pack more transactions, you actually get better reward. So this is like a game. It's in game theory, in where if you leave everything to fluctuate, then you can actually game the game in a sense. So what's interesting about this is that if you can actually go and look into the particular transactions. Okay, so let's say that we want to this transaction, which is like a transaction. We don't care really much about it. But the thing is that well, this is a successful transaction. This transaction is not waiting for it to be processed. This transaction is already done. There's transactions that are waiting, and if you say I'm going to pay a very low fee for it, some miner may say I'm not gonna get it anyway because there's some other transactions that are more interesting to be executed, and that usually happens pretty much in the Bitcoin network also. So the more that you pay, the faster you get enough confirmations to actually say yes, this transaction is a go. So what you can actually see here is that this transaction belongs to this particular block, and it has also an internal Uniswap contract. Uniswap is a liquidity pool. It's being used to provide financial services, specifically to those that need the money to perform transactions in exchanges and all that kind. So it's pretty normal to see this type of transactions happening between wallets from Binance, from FTX, or other exchanges, and happening and see happening here. So as you can see, you have the actual value and the transaction fee. So 0 Ether was actually transacted in this transaction, but there's still some fees that have applied for this particular transaction. And the reason why is because essentially you have your gas price, which is the amount of execution requires computation. So what you can see is that you can see the amount of limit, the amount of gas that the transaction used, and the base fee for it, blah blah blah, and also the burn fees, the amount of ether that was burned for this transaction to happen. So what really happens here is that, hey, we are executing a function that is swap exact tokens for ETH. You can actually go to the Uniswap contract and actually look what this function means and what every single input means, which in this case is amount, the amount in, the amount out, the path of the transactions, and essentially where all these ended up with. So to give you an idea of the type of information that you can actually get here, but the big question is, why do we need external solutions to actually be able to process this kind of stuff? The reason why is because these type of solutions, you have to essentially download the entire network. This is me running a node, a Ethereum node locally. I'm using this node in a way that is actually not a full node. You can actually run a full node. I synchronized the full node just to know how much time it could take on my machine, and it actually takes 4 days to synchronize the entire node intake, roughly around 700 gigabytes or something. Now I'm running, I'm essentially running a light version that it also have the headers, so I can actually show you how this works. So now when you think about it, what you have here is a analytic service, Why this is important? Essentially, because when you move money from one way to another, some things may happen. For instance, if you move 21 millions straight to Coinbase, which is an exchange, that may mean that the ETH price may go down because these people is gonna liquidate those assets in the exchange. So this type of information is actually very interesting. So that's where this gets interesting, because all these contracts actually mean something for the network. So let's talk about this particular transaction. This particular transaction is $6 million, and it's an NFT, a non-fungible token. These are interesting because even Wired is talking about this kind of stuff. It is essentially a contract that allows to transfer ownership for something in the database, in the blockchain, and it's transferable between people. But when that token is created, it's unique. So if you bind that to a digital asset, for instance, to the cryptographic signature of a digital asset, essentially it says that the token for that asset is already taken, and now you own that token itself. So that's why these type of things are being sold for like $6 million. Doesn't make any sense in a sense. But there's more interesting things that are happening on this behalf. Like, for instance, in this case, this economist was actually doing an example in which she bought a diamond, she destroyed the diamond, and she wanted to know if someone is able to buy the token that represents the digital version of that broken diamond. And as of yesterday, what was the last time that I looked, the actual price that someone is willing to buy that token is for 11 ETH, which is essentially roughly like today's price of 36K or something. When the actual diamond, the diamond that it was broken in the process, was only 6K US dollars. This is a pretty interesting example for anyone interested into the part of the in the financial ideas that this can happen, and this can happen. So because understanding this type of information, it's going to be interesting for us to show you how these all binds together to actually build a whale detector. The idea here is that we are going to be emulating that concept, that Twitter account, in where we are going to be looking for a specific type, a specific profile of transaction. And then we are going to be adding the ability to notify when those things happen. It's a very, very bare bones concept, but the idea is to understand how everything binds together and why external solutions are necessary for this kind of work. So without further ado, let's go to Visual Studio. So the very first step that you need to go with is actually import the data, or at least the interesting data, because essentially the blockchain is so big that it's interesting sometimes just focusing on the part that you actually need to work with. So as you can see here, this is pretty boilerplate just to work with RavenDB. We create a document store. You will know everything about this. We figured out what's the last process. We live at a market, so we know what's the last block that we have processed. And essentially what we now do is this. We create a client using Ethereum to be able to access, in particular, right now, to access this, which is my node that is synchronized with the blockchain, with the current state of the blockchain. There, external, for those not interested in running a node, there's actually versions of this that you can actually, there are projects out there that you can actually query the same information straight from them and not having to run the node. But in a sense, because I'm running localhost, I will just go with it. Infura.io is one of those projects out there. So essentially what we need is to define the concept of the transaction that we care about. Because in our case, the more important thing for a transaction is because the transaction is embedded into a block number. And because we want to track the movement of money between wallets, we want to know from where the money moved to where the money moved, and also the amount of ether that particular transaction has transacted into the system, have moved from one wallet to the other. We are not interested in fees. We're not interested in gas prices. We're not interested in essentially nothing else. So the how essentially you do that? Essentially, because this is I mentioned that this type of database is actually pretty slow. So if you are going to be asking with the amount of blocks that get generated and all that, if you when we finish the talk, we will publish a version, a GitHub repository where you actually can look how it was developed, and there are different versions of it, like the slow version and the fast version. What we are going to show right now is the streaming version, which is faster than Go Ask with async calls every single time, which essentially what will create a block processor which match a certain criteria. For us, the basic criteria is that we are going to be defining whale transactions over 1,000 Ethereum. That is roughly $3 million, more or less. When such a transaction is found, then we are going to be inserting it into the database. And essentially what we are going to be doing is the usual stuff. We are going to create the object and store it in the database, update the marker, and done. So pretty boilerplate work, is simple. So essentially what we need to, what we will find is that we will have this database that has collected all the transactions that are of interest for us. And we can actually go and look how it looks like. So we have these transactions from to and the amount of ether that we have. And the reason why you do that is because essentially you then want to query. You want to query this stuff. So say that from transaction infos as T, where the from starts with starts with the dot from, it was something like 0x to be whatever. So we want to actually, no, I think it's this one. I think it was this. So the concept is that because you need fast access, you need to be able to find stuff fast and to react and being able to analyze this information. It doesn't make sense to have that on an external storage that is costly to query. There are actually projects out there that are building these and providing this type of service, this type of query capability as a service. So there's an actual economy around understanding how the blockchain behaves. There are research companies that are doing that also. So because we are doing this, we are able to track every single transaction that is of interest for us. And then because of that, then we can go and actually go and build a system that will do will tell us, will send us a message every single time one of those transactions happens on a location of interest. For instance, if you are in trading and you want to know when there's a potential liquidation process going on, you want to know when transactions are getting sent through to Binance, when big transactions happen going to Binance from external parties, because that may signal a big sell-off in the market. So essentially what you do here is we create a few interesting indexes on top of these data, because we want to know single transactions. Transactions. We want to understand, okay, how many transactions are over a certain limit monthly. So if you have an address that is moving money to a particular place, and in this month moved more than 2,000 or 10,000 Ethereum, which is roughly 100 million, that is a movement that you want to be aware of. Okay, so you can do essentially this by day, which is essentially a MapReduce, and where you take all the transactions, you essentially mark, and then you essentially group over the date to get that information. The same happened with the monthly transactions. So you want every big big spender or big mover in each per month. So in a sense, it's similar to the top 10 in the 24 hours that Ethers can have. So because of that, and because we actually want this information to actually be stored in the databases, and we can actually create subscriptions on top of that, so we are actually being able to notify when that happens. So the output of the reduce is going to be stored in a collection. Let's go and check. So what you're seeing here is that the outputs for that specific thing. So we see that this particular from account just sent $100 million in a single transaction. But there may be others like this one, which is this month, in this day, actually moved 6 transactions for 150 million. So this kind of information, it's useful to understand what's going on, and you can essentially build million of different endpoints to actually get this information, which is when it is interesting to act on it. So the idea is, because now we have these MapReduce indexes, we can actually go and ask for it. It's like saying, okay, yes, we want to know, we want to be notified when when a particular transaction happens, and because of that, essentially what we are doing is we are saying, okay, we create this particular transaction, this particular subscription, but in this case we don't care about all of them. We really don't. So essentially we want every case where there are multiple transactions that are over 10,000 Ether. So because of that, essentially what we do is when this matches, when this filter matches, we are going to be sending to us through Telegram this information. The same in the case of the monthly. It doesn't change much, but for the monthly, we are actually more interested into like the big money. It's like 20 transactions and over 100,000. And for single transactions, we want to know every time that one of those transactions happens. How can you extend it? You can actually, there are known addresses out there. We know that certain addresses belong to Binance, to FTX and the other exchanges. We can actually track that information and say, okay, we want only those that belongs to these sets of addresses. the many ways we can make this better and tailor for a specific type of application we are building. So it essentially what it does is send a message through Telegram. We're going to be demonstrating it, so see that this works and how it works. What essentially would happen here is that we are going to be running this system here. This is gonna open those subscriptions, and essentially we are going to be start importing, and we are continue processing. I stop the processor instead of leaving it live in order to ensure that we can actually find whales in here. So this is what happened. We just got a transaction here. This is our timeline, because these two transactions actually, and here we hit all those conditions because these are big transactions. Okay, so these two transactions actually generated an update in the monthly whale and the daily whale too. So we are also getting those. The idea is not for you to get it on the Telegram, but to notify other systems that are actually going to get this information, look up what's interesting about those particular. So you can actually be the chain of a system that is going to be doing this data gathering that is interesting to you to actually act upon. So as you can see, this type of solution, when you have, we actually did this with the Jan in like 1.5 days or something, not even full time. So the thing is that you can build this type of tools pretty easily without much trouble. So let's continue. So essentially, when we are going to be putting this, so you can actually, if you want to look at it, we're going to be leaving this code for you into the Ethereum scanner link here. And for now, let's move into questions from the audience.
While we're waiting for additional questions, I want to make sure that I'm following what you're doing here. You threw the data from the blockchain into RavenDB, and then you threw that into MapReduce index, and then you operate on that using a subscription?
Exactly.
Do you have any numbers on the latency between an event on the blockchain and how soon do you see that on Telegram?
The blockchain is so slow in a sense that these type of transactions happen like once every 35 seconds or something. Latency that you have here is sub-second easily, because essentially what you have is like whenever the actual latency happens here, which is essentially your node understanding that, finding out that the consensus was arrived on a particular node. So because transactions in this happens, as you can see, we have 2 transactions here in the lapse of 10 seconds. So this is so slow that we actually ran this for the entire thing in just the lowest thing that we could find in the RavenDB cloud with the Jam. So and you cannot actually see the difference. Most interesting things would be if you just, for instance, in the case of Ethereum, and this is interesting, it's an interesting thing, is you can actually create a provider that is going to be caching this information straight into the database instead of you having to pull this stuff. Essentially what you have is a provider that is going to dump the entire database into there. So everything that gets retrieved is gonna end up in your database. And you can actually process the entire blockchain and start the entire blockchain for processing if you want to. that's actually a different way to handle this. Instead of saying, oh, I'm going to be collecting the events that are of my interest, what I will do is essentially say, no, I don't want to do that. I just want to have everything in place. This is essentially what I did, for instance, in the case of the Bitcoin database, which is smaller. I would just add everything and then do analytics on top of it directly. And knowing that you have several type of blockchains that you can store in your database, and you can cross-reference, because there are transactions that are actually talking between two different databases, two different blockchains. So it becomes pretty interesting to understand the behavioral patterns where one thing moves to the other, and how that impacts prices, for instance, at the Ether level. So for example, for trade.
That's a whole different issue because of I'm talking about trading with the latency involved in blockchain transaction makes a lot of the typical high frequency strategies irrelevant.
Don't work.
Yeah.
But this type of information is not for high frequency. High frequency is more about the prices themselves. So you're actually going to be hooked up into the exchange and taking decisions straight on that level. It's not at this level that you're working here. In here, you're working more trying to understand, you know, if there's someone that push information, a lot of Ether into an exchange, it means that you're probably going to have a liquidity spike, a volatility spike happening in that particular exchange pretty soon. And it's actually interesting because this actually happens. There are whales that want to move the price, and what they essentially do is they transfer to the exchange to signal that something is gonna happen, but then it doesn't happen because it's not their intention, so they are gaming the system. It's pretty interesting how the availability of these kind of tools and the availability to being able to just look up even how much money you can actually go to the wallet from Binance, the hot wallet from Binance, and know how much money they have in there. It's very, very interesting because this is one of the downsides. It's an upside, but it's also a downside. If you want to stay yourself hidden, if you're a whale and you want to stay hidden, you can, because everything is public. If I find that your wallet has a certain your wallet, then I can track you forever and ever. So if I have good analytic tools in where I can actually follow the money, there's no way you can hide that money. There's contracts that try to do that, which like essentially how to put it in this way, they're going to put a lot of money from different people. They are going to scramble it together, and they're going to be distributed in different accounts, in different wallets. So so you cannot actually, when you get a thousand Ethereum, but you get that Ethereum separated over time, but still that can be gamed. Well, at certain levels, you can create very advanced pattern analysis software to actually figure that out.
In this case, you're talking about blockchains like Bitcoins or Ethereum.
Yeah, in any blockchain, you can actually do that.
How about Monero, which is supposed to be a private? Really, I can also track the money.
But you can actually look at the Monero too.
No, I know that I can look at that.
The question is, the consensus is there.
No, the question, I know that I can see the transaction in Monero. The question is whatever, and this is one of the selling point that's going on there, that you're supposed to have privacy. That used to be one of those things that you would go to Bitcoin for, until people realize that that's quite the opposite. But,
yes, the problem is the following. Everything is breakable at the point that when you have an external service. Let's say that this is an example I always use. So you want to stay anonymous. So you have this unnamed unnamed wallet. Now, if you make the mistake of sending that to someone, and that someone leaks your identity, Now, anyone can actually pull from that specific knowledge and move down to wherever you are. I don't know exactly the case of Monero, how they try to mask that situation. But the point is, when the data is open, there's always ways to, and if you have a certain piece of information, to actually move backwards in time.
It looks
Essentially, this is interesting because MIT, for instance, I believe it was 5 years ago. Yes, 5 years ago, I think. MIT was able to actually map, they built a pattern recognition algorithm, specifically aimed to figure out where the stolen money had gone from the exchanges. So essentially, this is the type of algorithm that anyone working in money laundering is, and even more advanced than what MIT may have pulled off, or at least in public. So the thing is, when something is public, what you need is someone to screw up. And when someone screw up, is exactly the moment that all that privacy goes poof. Okay.
Okay.
So you have a privacy by design, unless you essentially trip over a problem. And that's where it becomes interesting. I really haven't looked into Monero details. So I don't know how they try to mask this kind of information. Probably it's a very advanced thing, if that's essentially what they do. And probably the attack surface may be very, very small. But never forget, everything that is built is actually hackable in some way. So you may end up in a situation when something actually, you transacted with something because you thought it was private. Eventually it got broken. And because it got broken, now you are in the open.
Okay. Okay. To the audience, do we have any questions? I think this is it. Federico, thank you so much for showing up and telling us all about this. Quite interesting.
You're welcome, everybody.
Oh, one second.
Hope you like it. If you have any...
we have a question. We have a question from
great.
Georgie, I think that's how you pronounce that. Which feature from RavenDB have you used?
The features that we use to do this with the John are pretty simple. We just open a session, we send the data in, and then we use three MapReduce indexes for collecting the aggregate information that we needed to send the Telegram messages. And then we use subscriptions, which allows us to keep a pointer, keep a cursor where the last things that happen, and when you start it, it's just going to be processing, continue where it left go. So then we are going to be sending through that subscription the information to Telegram, and Telegram essentially to here.
Okay. If you have any further questions, feel free to ping us, and we'd be happy to give you the details. And can you show the link?
One more question.
Awesome. Oh, that's an interesting one. Georgie is asking, does would time series be useful here for something?
Can you repeat that?
Would time series be useful here for something?
Yeah, probably not for this scenario. Then the interesting thing is why we choose this scenario, because it was something that we could actually demonstrate, and you could actually go and do like in 10 hours if you are inclined to redo this. Even though we are going to provide the code, And there's also a README in the importer. This is interesting for everyone that wants to try it out, just running get here like I'm doing. There's a README there that that explain how to set up this to work. Because this actually takes a lot of time if you're not into it. But the thing is that we did this because it was easy for you to just replicate it just from memory if you want to. But more advanced scenarios would actually require time series, because you actually want to be able to understand, for instance, statistics of, for instance, you may want to have the prices or the amount of burn fees over time. So if you are going to be collecting that, it's actually easier to put that into a time series that you can actually ask questions like moving averages and other statistical questions directly on the sequence of data, which is not probably what you would do directly on the documents themselves, or the transactions themselves, as we did here. There's also another reason why you may want to have that stored in time series, and its efficiency in the storage and in the ability to process that. Because if you are going to be writing an entire JSON document just to store a single integer or a single floating point or a single decimal, it doesn't make much more sense. What you could actually do is, like, for instance, in this case, we did the aggregate for every day or every month. What you could actually go and say is, we want to keep a time series, and this is a good example. It's a good example that you could actually do, which is instead of storing the specific transaction for a particular wallet, just store the time series when those transactions happen. So then you can run, for instance, a range query in which you can say, oh, I want to know how much it was transacted from this day to this day, or this minute to this other minute, which is more is better tuned for dealing with time series than for dealing with documents directly. Hope that makes sense. The question makes sense to you.
Okay, great. Great. So again, Federico, thank you. And any further questions, send us an email.
Thank you, everybody, to be here. Hope you like it. Bye-bye.
Bye-bye.